Take it away, Claude.
All right. Well, good evening. Welcome to the East Valley Astronomy Club for February. We're glad that you're with us. Currently about 60 folks, which is really great attendance, and we appreciate that. I'm sure it'll grow in the next few minutes to even more. But we're glad that you've joined us tonight, and we have some fun program for you. This looks like an early picture that I would have taken with my telescope, but this is from the James Webb. It's their early alignment image. I'm thinking it also looks like M7, but that's just kind of my memory of that from the summer. But it's kind of nice to see that the Webb is working and everything seems to be going well. For your officers and board, I'm your president, Claude Haynes. The vice president's position is still open, and we would appreciate any of you who wish to apply for that. I'm sure Tom would be very grateful for that. Our secretary is Gordon Rosner, and our treasurer is Alexandra Nachman. And then for the board members, Dave Kosho, John Kester, Bill Peters, Brooke Schofield, and Derek. And these are the people who manage the club on your behalf, and so we would like to hear from you. This afternoon, that image got improved. The last one released is now of a more cohesive looking 18 points of fuzziness, but at least that it's coming together, and we think that's what we're doing here. So we're glad that we're able to join with each other, even if it's just via Zoom and not live quite yet. But we would like to hear from you. So if you have any comments or suggestions, you can send them. Many of you have my direct email, or you can look on the website under Contact Us. If you have some information that you would like to share, or you have questions about the club, please look on the website under Contact, and then there's a president, vice president, secretary, etc., where you can send us emails, and we'll be glad to respond to you that way. Quote of the month: if I've ever made any valuable discoveries, it has been due more to patient attention than to any other talent. It seems like Isaac Newton was extremely modest, saying that he was standing on the shoulders of giants. I don't think this is reflective of his ego, however, but we would like you to help us support the club by renewing your membership so that all of us can work together with our patient attention to help each other to develop our talents. A couple of quick announcements. The Tempe Public Library sent me some information. They have some lecture series every couple of weeks. There is one tomorrow on the stellar graveyard, black holes, neutron stars, all the things that kind of come from stars as they age. These are at the Tempe Public Library. They're at 3500 South Rural. The cross streets are Rural and Southern. It's room A at 11 a.m. There's no reservation required. And if you're interested in any of those topics, and in the coming newsletter, we'll mention the ones from March. But there is one coming up tomorrow if you are interested at 11 a.m. And then we have a member presentation from Bob Buchheim this evening. And Bob, I think if you would just go ahead and share your screen and take over, we'll move on from there.
Just need to unmute Bob.
Okay. And there it works. Screen sharing works. Perfect.
Miracle of technology.
Yeah. Okay. Hi, everybody. This is more of a sales pitch than a presentation, but when you share a view of something through your telescope, you wonder just what is she thinking as she stares into the eyepiece. Now, there's a clue in this picture. Note that all of these brownies, they each came with a notebook, and they're recording their observations, just like Galileo did. So what she's thinking is, can my observations contribute to science? Admit it, some of you have had the same thought from time to time, and you probably cast that thought away because real astronomers have giant telescopes on the top of mountains or in outer space. So how can we possibly compete with that? Well, we can't. We can't compete, but it turns out we can collaborate. If you divide the cosmos along 3 axes, on the vertical axis, some things are constant, they don't change. Others are dynamic. They move, they get brighter or dimmer, their color or their spectrum changes. On the horizontal axis, look at the time frame of those changes. Sometimes they happen very rapidly on a short time frame. Sometimes they take decades, maybe millennia to see the change happen. And on the axis running in and out of the screen, some things are faint and some things are bright. The big professional observatories are really designed to make exquisitely precise measurements of faint objects. But there are so few observatories and so many astronomers with really good ideas that time allocation committees can't grant more than a couple of nights per year to most projects. So their sweet spot is making a small number of observations, repeating them infrequently, sort of a one and done philosophy to observing. And it makes it really difficult for them to deal with dynamic phenomena that require time series observations continuously over weeks or months or years. And there are quite a few such phenomena in the sky: variable stars, asteroids rotating, stars blowing up. And many of those are bright enough that you can observe and measure them quite capably with our small backyard telescopes. And that's the part of the cosmos where we can productively collaborate with researchers to push the progress of science a little further forward. We don't have time allocation committees that restrict our use of the telescopes. We can squander all night, every night for a month on some object if it particularly interests us. And we can partner with people on the East Coast, in Hawaii, in England, in Japan, to keep some object under 24-hour surveillance. The sun never rises on that object that way. And there are more of us than there are of them. So the answer is, yes, indeed, amateur observers can make a contribution to science in this way. And if you're curious about that, I invite you to participate in the annual symposium of the Society for Astronomical Sciences that will be held in Ontario, California on June 2, 3, and 4 in person, so that you can put a human face on these people that you've only seen on flat screens. You can discuss science and life in the bar, and maybe push the glass aside and scribble some equations on a napkin, just like we used to be able to do at symposia. For people who can't travel, we'll have an option for interactive online participation that will bring you most of the same effect of being there in person, except the bar. On Thursday, June 2nd, we'll have 2 workshops. One will be a deep examination of using CMOS cameras for photometry to understand the differences that they have compared to CCDs and how to take advantage of their unique features. The other workshop will feature a handful of professional astronomers describing projects that they wish we would take on, that fall in that sweet spot of relatively bright, demanding a lot of telescope time for small observers. They'll present the science cases, the observing plan, and discuss how we might participate in those projects. And then the technical presentations will fill the days on Friday and Saturday. If you're already involved in research or education projects, Wayne, Woody, Tom, Hanan, that means you. Inquiring minds would like to hear what you've been up to in the dark. The call for abstracts is open. They're due on March 20th. Get them in. For all of the details, the website is socastrosci.org. And I hope some of you will decide to join us either in person or online. This is really the premier annual event devoted to small telescope astronomical research, and it might send your enjoyment of the hobby in a whole new direction. If you have any questions, feel free to email me at oca_bob@yahoo.com, and I'll be happy to help you out. Look forward to seeing some of you there. And Claude and Gordon and Tom, thank you for the time. That concludes my prepared remarks.
Thanks, Bob.
Thank
Okay.
you. Share screen, I'll go back here. All right. And if you have any questions or some comments or information, you can use the Q&A button. Kind of, if you move your mouse, it may show up. Sometimes it disappears. Tom is monitoring those. Or you can use chat, but if you use chat, be sure that you're going to choose host and panelist or a chat to everyone. And that's kind of an odd option. And that's why we think that the Q&A would be the easiest, but we are monitoring those to make sure that we'll be able to answer your questions if any of those come up. Couple of small things there. Greco is open for public viewing Saturdays only from sunset till 9:30. This week only, Tom Marston is bringing the EV scope by Unistellar that is owned by ASU. We'll try that for a demonstration. He'll be there around 7 to 8:30 or so if you want to come and view that. It is Tom, why don't you give a better definition than I would give of what this little beast is?
Okay. In a nutshell, it's a telescope that has a CCD camera that takes images in real time. And if you have steady seeing and choose to start stacking those images, the image you'll see on your phone or in the scope's eyepiece is a stacked image of what the telescope is looking at. So you could, brings out the nebulosity and faint stars really well. And the thing we think would be attractive for public outreach telescope viewing is that the audience connects to the telescope with an app on their phone. The telescope puts out a Wi-Fi hotspot, and people who have that app on their phone can connect to that hotspot, and whatever the scope is looking at appears on their phone, and they can download their very own image instead of having to take their phone to an eyepiece of an optical scope and fiddle around for 2 or 3 minutes trying to get it to focus in their phone. So we don't know what the response would be from the public for downloading an app on the spot and connecting. So this is the first trial to see how it goes.
Okay, great, thank you. And if you want to come and test it out or help us to judge how effective that is with the attendees here, feel free to. That would be a fun thing to do. Another opportunity coming up, if you don't have enough hobbies, you can attend the Gilbert Outdoors Expo and learn about fishing and boating and hunting and all of the other things that are other outdoor activities besides astronomy. That's coming up on Saturday, March 5th, 9 a.m. to 2 p.m. We will be doing solar viewing at the observatory, but it's a fun activity for families. And we certainly would recommend, again, if you wanted to come out to the park and have some fun, Saturday, March 5th. And then the Messier Marathon hopefully is coming up on Saturday, March 26th. I'm saying hopefully because at the SAC meeting, that was what Tom Curry said, is that they hope they can get everything set up and organized for that. I would say check the SAC website for details. I have to tell a small story. I was talking with a friend and I said we were talking about the Messier Marathon, and he replied, "Oh, it's good that you're getting some exercise." No, it's not that kind of marathon. If you find my body next to the jogging trail, that is not where the murder took place. It is a contest to find 110 things that we shouldn't be looking at anyway because they're not comets. And it's lots of fun. And I think we've missed it the last couple of years. So if SAC is able to organize it, please check their website and come out and have some fun viewing with your buddies and looking at all of those faint fuzzies from Mr. Messier's list. That brings us to our speaker tonight, Nat Butler. So Tom, would you please introduce our speaker?
All right, thank you, Claude. It's my honor to introduce Professor Nat Butler, ASU. He's an astrophysicist interested in the properties and evolution of the early universe. His current research focuses on experiments to observe and study astrophysical explosions and to use these to probe the first stars and galaxies and their environments. So please welcome Nat.
Mind if I switch your screen here?
Yeah, just start sharing.
Okay. Okay, can you see my screen? Same title?
Looks good.
Cool. Well, hello, everybody. Good evening. I want to shift up one of my standard talks and maybe make it a little more interesting for you folks. So I'm going to talk about things that blow up. This is a picture of a gamma ray burst, or an artist's rendition of a gamma ray burst. And I want to talk more than I would normally about software, and particularly the relation to small telescopes, and maybe give you some ideas for software you might try out, particularly those of you who are into astrophotography. And so maybe you can get some connections. I'll sort of describe what has become essentially a software problem for me because of its complexity and sheer amount of data. Okay, and so to start off, let me make a statement. Okay, a new window to the universe is opened. And so this is a clue to what I'll be talking about. And in a moment, I'll start with a quick video just to sort of set the pace. But I want to talk about two sorts of classes of things. I want to talk about gravitational waves. So the video I'll show in a minute is going to be taking us back 5 or 6 years to the first discovery of gravitational waves. I want to talk about the connection of those to gamma ray bursts and the challenges associated to sort of drawing out and understanding those connections over the last several years, and how we have many, many very much still open questions. And I want to pose some of those as sort of exciting software topics. Okay. At any point here, ask questions if you want to. I think, Tom, maybe you can alert me if any questions come up. Feel free to cut in and I'll answer away.
Okay, will do.
Okay, so let me start with this quick video.
1.3 billion years ago, in a galaxy far, far away, two black holes merged. As they violently spiraled into each other, they created traveling distortions in the fabric of space-time, gravitational waves. In the last 1/10 of a second, the energy released in these waves was 50 times greater than the energy being released by everything else in the observable universe combined. That's like an awe-inspiring kind of energy. After spreading out through the universe at the speed of light for over 1 billion years, the waves reached Earth, where they stretched and squeezed space such that two light beams traveling in perpendicular pipes were put slightly out of step, allowing humans to detect the existence of gravitational waves for the first time.
Okay, let me focus in on this last little picture here. So I hope this refreshes people's memories a bit about this big discovery several years ago now. And this is a shot of the gravitational wave signal, which is a chirp. I'm playing it at the original frequency and then at a higher frequency. You can turn up your volume a little bit if you're having trouble hearing it. So the plot shows the time history of this event. It lasts about a half second. It was detected in 2 locations, one in Washington and one in Louisiana. And then the color shaded areas show the frequency spectrum. So as this signal sort of increases in intensity, it also increases in frequency. It creates a chirp. So listen for that for a second. Okay, and this is a detection of a gravitational wave event. I'll talk more about what those are by LIGO, the Laser Interferometer Gravitational Wave Observatory. And it's detected by 2 of these observatories at the same time. So coincident signal, same shape. Okay, let me keep going. Okay, so that was, I think that was the first event that was detected back in 2015. This plot here shows events collected over the next couple of years, and it's shown with a y-axis that's distance from us, so billions of light years from Earth, and a similar axis on the x-axis, which is megaparsec, so another measure of distance. So 2 different ways of thinking about distance, right? The events that happen here, good, my cursor works. So we have events that are very nearby that have to do with the merger of neutron stars. Those events can't be detected at such great distances as some of these other events, which are mergers of black hole systems. Okay, so the sort of brightness of the signal can depend on what merges. But the overall structure of the signal, that chirp I showed, is the result of these 2 compact objects orbiting each other, losing orbital energy as they emit gravitational waves and eventually spiraling into one another and merging. Okay, so I'll say more about this in a second, but as of the first few years of LIGO, they had a handful of these events. A very important one, I'll stress in most of my talk here, this event in August of 2017. So you'll notice the dates of these things, 2017, August 17th. These things, just like I'll show gamma ray bursts in a second, are labeled by the date that they happened, right? So this was this event that lasted several seconds, occurred on this date, okay? And this one was the most nearby. This is the one I'll mention more because it led to the Nobel Prize that year in 2017. These other events, these black hole events, are more commonly found in LIGO. Since this time, we've had a total of 3 LIGO runs. They find about 3 of these binary neutron star events a year, and none of them has led to quite the level of discovery and follow-up and excitement as this first event. So a lot of the work that's happening is to try to find out where these are and how to get more of them. If you look a little more closely at this, so let me talk about the kind of picture that's going on here and focus in on that specific event of 2017. So this is merging neutron stars. So a little picture like in the upper right here. So 2 compact objects, neutron stars, left over from stars that evolved and left behind those cores in a binary system. And due to the loss of gravitational energy, they merge, producing this signal that I showed. So I'm gonna get my cursor here, right? This sort of ringing signal with it, which has a chirp at the very end as the 2 things merge, and then a ring down, a sort of decrease back to 0 as the final object is produced, okay? Now, what was really important about this event back in 2017 is it wasn't just detected in gravitational waves. So this event was very special in that we managed to chase it with larger telescopes, and we found the electromagnetic counterpart to this event. So this is an NGC galaxy, a nearby galaxy. And then here was a new point source, which was associated with this gravitational wave event. So a new source was detected in an image, I believe, with the Magellan telescope. That source then faded away. Team I was working with also managed to point the Chandra X-ray telescope at this system, and we found an X-ray source also fading at that position as well. Okay, so this was the first electromagnetic counterpart found to a gravitational wave source. In a sense, this is a huge vindication of the theory that predicted gravitational waves because it proves that they're astrophysical. It ties them to the merger of massive stars or neutron stars at the end of massive stars' lives. And it sort of completes a picture, right? And so The 2017 Nobel Prize in Physics was awarded that year. This was all kind of hush-hush for several months. I was one of 60-some teams working on these kinds of observations. I had a telescope called Gemini that I was using on a nightly basis to try to build up nice time histories of this source. And we were all, super secret because of the decision made fairly early on after this event to generate the awarding of the Nobel Prize. Okay. So it was a cool event, but we also learned a lot of impressive stuff about our universe from this event. These are the three winners of the Nobel Prize. So Ray Weiss, who's one of the foundational members of LIGO, sort of one of the major people that conceived of the project itself and the possibility of doing this kind of observation. And then a theorist, Kip Thorne, who you may know or know of, and Barry Barish, who had a lot of work making LIGO actually happen. Okay. So this was the confirmation of gravitational waves essentially by seeing, what I mean by confirmation is seeing the light, the electromagnetic signal from the gravitational waves as well. Okay, and it's a huge amount of work to have gotten to this point. So it was literally generations of scientists and engineers who were working on LIGO. When I was a graduate student 20 years ago or so, I had other students who were major people involved in LIGO. Many of them made contributions, left the field, maybe stayed in the field, but it was very few of those folks who actually made it all the way to the end to this kind of discovery and payoff at the end, right? It took many, literally generations of scientists to make such a project happen. Okay, and scientists working on the theory, including people like Stephen Hawking, Einstein, of course, and then people like me working on the observations from the ground to chase the electromagnetic signal with our telescopes, our networks of telescopes, and the systems we have for sharing that information. Okay, so gravitational waves. So this is a prediction of Einstein's general theory of relativity. It was a prediction that even Einstein was rather uncertain about and waffled on quite a bit, whether these waves would actually propagate outward and be detectable signals. But the overall idea is you have two very dense, massive things creating warps in space-time, creating ripples as they pass through space-time, sort of like the little diagram I have here. And as they merge and come closer together, that distortion becomes larger, and due to these predictions from general relativity, the wave signal propagates outward. As we'll see in a moment, it propagates outward at the speed of light and is in principle something we could hopefully hope to detect at Earth. Okay, and then as I showed in the video, this is how we go about detecting it. This is pretty amazing in the sense that this is a realization of what was a thought experiment conducted by Ray Weiss in a class in 1967. So how do you go about detecting gravitational waves? So the idea is the signal comes through, it has a transverse structure, but it's a very, very tiny signal. And what you need is essentially the ability to measure something that's a change on the fraction of the size of an atom. And you got to be able to measure that over very long distances. So what LIGO is it's these two perpendicular arms. There's, this is the one I believe in, did I say here? I think this is the one in Louisiana. Could be the one in Washington. Actually, it looks pretty dry up there. So this is the one in Hanford, Washington. So each of these laser arms is about 4 kilometers long. And what happens is you use interferometry to combine those beams to look for very small changes in the length of one beam with respect to the other. And so as the gravitational wave passes through, it shrinks one arm a little bit, and it shrinks or increases the other arm a little bit by essentially shrinking or enlarging space-time itself. Okay. So that's the idea. And the amazing thing is this thing actually was built, and it's being replicated in several other places around the Earth. Okay, so kind of amazing. This thing was built, it actually works. And now we're in this period of multi-messenger astronomy where a new window into the universe is opened, this window of gravitational waves. Okay, it's kind of like sound, right? It's a new kind of signal. So let's think about the kind of signals we're used to. Here we are as humans. This is the electromagnetic spectrum. we operate most of our lives in this little very narrow region, right? The visible portion of the electromagnetic spectrum, right? Which happens to be a part of the electromagnetic spectrum where water transmits really well. We evolved from creatures in water, so our eyes work really well with visible light. There's some other windows where light gets through the atmosphere pretty well, like in the radio part of the spectrum, a little bit of the infrared and UV, but not much. A lot of these ranges, as you go into, let's say, the highest energy part of the electromagnetic spectrum, so this is shorter wavelengths or higher frequency or higher photon energy. As you go into the ultraviolet, the soft X-rays, the hard X-rays, gamma rays, most of that light, thankfully, is absorbed by the atmosphere, right? But a lot of really interesting physics emits light at those kind of frequencies. So if you have things like satellites in space, we can look for those kind of signals. And part of the story I want to tell is how those high energy signals are related to explosions at the end of massive stars, and I want to connect that back up to gravitational waves. Okay, so quick point here. Literally, we cannot see most light emitted in the universe, right? Light isn't just visible light. It spans everything from radio waves to gamma rays. So quite a range and a lot of really interesting physics, which depends on the size and the amount of energy of the thing doing the emission happens at different parts of this spectrum. Okay, let's talk gamma rays. So if you imagine for a moment that you had gamma ray eyes instead of visible light eyes, and you looked up at the sky, as we often do, you would see something kind of like this. This is a little unfair. This is what a telescope called Fermi saw after integrating for a couple of years, right? So you'd have to look for a while to see this, and pretty big eyes, but let's imagine this game. It's also in sort of weird coordinates. So this is a set of coordinates, galactic coordinates, where along the x-axis is the plane of our galaxy. And if you go away from the x-axis toward the poles, what you see essentially are directions out into intergalactic space. And what you see are these little point sources are other galaxies, or at least the cores of other galaxies. So this bright stuff, the emission, is the plane of our galaxy. Can call out a couple of other things here. Some of the point sources, they tend to be exotic things like supernova remnants, pulsars, things where physics are very extreme and particles are accelerated and produce these high energy gamma ray photons. And if you look away from the plane, those point sources tend to be supermassive black holes at the centers of other galaxies. So things we call AGN, quasars, those are gamma ray emitting sources. And you can kind of get a sense, if you had gamma ray eyes, of what the sky might look like, right? Our galaxy is super active. And then in a sense, you can see other galaxies because of what's happening at their cores. There's also really interesting kind of diffuse gamma ray emission kind of flowing out from our galaxy, which I won't talk about. Okay, well, what I do want to talk about is, so I said this is like a 2-year exposure. I want to talk about what gamma ray eyes might see in a much shorter time scale. So take a look at this plot. On the right is a time history. So it's like the entire flux in gamma rays of the night sky. Okay, and remember, it's comprised of that red stuff that's the plane from our galaxy, but it's also comprised of all those little point sources. And notice that during this about 10 seconds that this is captured, there's a hugely bright source that goes off. It lasts at its peak, maybe a second, right? But you can see in the little picture on the left, the map, that source for about a second is the brightest thing in the observable universe, right? So that would be pretty crazy if you had gamma ray eyes. You'd go outside, and an event like this happens about once a day, a so-called gamma ray burst. So you would literally see kind of a flash of light lasting maybe 5-10 seconds, but it would drown out everything in the night sky, right? So just think for a second how different that is from what our night sky in the visible looks like, right? So maybe if you're lucky, you might see a supernova in your lifetime. They happen about once per century per galaxy, right? But they're very, very rare. On the other hand, this is an event that happens about once a day. Okay, so this happens to be a gamma ray burst detected by the BATSI experiment. Now, these things go back to roughly 1967, where they were detected by chance by top secret experiments that were sent up into space to monitor nuclear test ban treaties. So the first gamma ray burst ever is shown here on the left. Up on the right, here's President Kennedy with one of the velador satellites, the watchman satellites. You can see in the schematic what they kind of look like. They're downward facing, they're looking down at Earth, right? But they also have sensitivity to things all around. And this kind of event was detected, right? And this is the first GRB detected, GRB 1967-0702, right? So that's July 2nd, 1967. And like the other one I showed, it lasts, you know, less than 10 seconds, okay? And then notice this date, detected in 67, published in 1973, right? So it took 6 years for this stuff to be declassified and to come into scientific journals. Okay, and for the next, oh, I don't know, 20 years or so, the number of theories to explain what this kind of thing might be far outnumbered any actual numbers of detected gamma ray bursts. So there were a lot of different ideas for what these kind of flashes of gamma rays might be, everything from signals from aliens to things within our galaxy to things cosmologically distant. Okay. Just a quick slide on history and what's happened since this time period. So over the ensuing decades, satellites were launched to study this phenomena. The first dedicated one I mentioned was BATSI, but since then there have been several. I worked in grad school on a satellite called HEDI, shown here. Currently, the main satellite we have is SWIFT, which is still active. And what they essentially do is they're up in the atmosphere, remember, because gamma rays don't penetrate our atmosphere. They're looking for these short pulses of gamma ray light. And then what they do is they get a good position on the sky for that light and they radio it to the ground. Okay, and that allows us ground-based observers to point our big telescopes and to try to study that event. Okay, and gravitational waves, LIGO, uses essentially the same network, the so-called gamma ray coordinates network, which you could even log on there if you wanted to get their messages. You could even submit messages once you sort of apply to the system. This is sort of our communications backbone, where we get detections of these sources, and as astronomers around the world, we share our results and keep the process moving. And this is a super fast kind of field. You know, the events I showed last seconds, right? We tend to observe within minutes, get big results within hours. If an event's bright enough, we might observe it for days, but oftentimes our work is all done in the span of an hour. And this is a system largely of robots. Okay, let me just say a bit more about massive stars, just to kind of, I won't go into this a lot, but just so we're on the same page. So, what's sort of happening with a star as it's evolving and it's burning up stuff in its core, you know, synthesizing heavier and heavier metals, right? Like a star like the sun is burning hydrogen to helium, right? And that's kind of the farthest it gets in its life. Eventually it runs out of that hydrogen and, you know, kind of peters out and dissipates. The more massive stars like this can burn metals up to higher and higher atomic numbers, so burning up to things like carbon, oxygen, nitrogen, silicon, and other multiple alpha elements like magnesium and neon, all the way up to iron, which is sort of the last stable nucleus. And as they're doing this, this is in a massive star happening very, very fast. A massive star might live 1 million years, and this final burning of these onion-like layers can be lasting, you know, minutes as we burn down to this iron core. And eventually, once you get to the iron, there's no more source of self-support for this star. So there's no more nuclear fusion that can happen to fight and you know, work against gravity. So the outer envelopes come crashing in. You get a bounce against this iron core, which can throw off the outer layers, producing a supernova. And then the force of that can also force the core into a compact object. So a neutron star, if it's massive enough, a black hole. And then somehow, we don't exactly understand the process, but in some of these most extreme systems, is that black hole is formed, an accretion disk is formed around it, like I show in here. And then you can get 2 bursts of radiation. That's the gamma ray burst along the poles of that compact object that's produced. That's the final pulse of gamma rays that happens, produces a gamma ray burst. Okay, and recall I talked about gravitational waves. That's like the merger of 2 of these compact objects. It's also thought that some gravitational waves are related to gamma ray bursts because the same kind of pulse of gamma rays can happen if there's material around one of those mergers as it happens. Okay. In general, this is sort of the life and death of a very, very massive star, something at least 3 times the mass of the sun, probably 10 to 30 times, where you really start to get exciting stuff happening like the black holes and the gamma ray bursts forming. Okay. As I mentioned, there are sort of 2 flavors of gamma ray bursts, and this is an observational statement. So this is a plot of the number of events of gamma ray bursts versus the log of their durations. So 0 in these units are events that last a second, right? So anything to the left of here is an event lasting less than a second. And right around here, about this kind of cutoff, about 2 seconds in, there's sort of a division between these 2 populations based on their duration. So you have the so-called short duration gamma ray bursts, which last less than about 2 seconds, and the so-called long duration gamma ray bursts, which can last 100 seconds. They typically last about, say, 10 seconds. So this is just a purely observational statement. There is obviously kind of evidence for 2 classes, but they do overlap, so maybe not a super clean separation. And there's been a sort of conjecture for many years that these events, the short duration ones, are due to compact object mergers, while the longer events are due to the massive stars, the sort of supernova events, which have more material around them, sort of more time for stuff to echo around. And indeed, in the sort of 2000s, with Swift and other satellites, very good, let me back up, very good observations of these so-called long bursts were found and proved quite conclusively that the nearest ones had clear evidence for supernovae. So you'd observe a gamma ray burst. If it was close enough, you could hope to measure the supernova signal about a week to a couple weeks later as the light from the blast wave of the supernova eventually catches up. And this is sort of a critical early measurement made in Arizona of one of these systems. So this is a gamma ray burst spectrum in blue, and then shown for reference is a core collapse supernova spectrum, which you can see has these sort of characteristic broad sort of wiggles to it. So this is kind of the smoking gun that these long duration bursts are due to massive star death. Okay, and then we've since then had a lot more evidence for this. Every time you see a gamma ray burst and you follow it up, it tends to be in the part of its galaxy where a lot of star formation is happening. So they're very intriguing, but very clearly linked to the deaths of massive stars. Whereas the short, harder to follow because they tend to be a lot fainter, tend not to be located in these star forming regions. They can be outside of a galaxy. They can be in much sort of quieter, older stellar populations. So that's more consistent with this picture of merging compact objects, right, which would happen after a supernova, but then maybe after an additional billion years or so that it takes for those 2 objects to, those 2 neutron stars or black holes to finally coalesce and merge. So that can be delayed significantly relative to what would happen for a supernova explosion. And as a result, the kind of signal you get from it is very different. So right, you have the potential of getting this sort of merger signal. And it's a much faster signal because the things are much smaller, the light travel times are much shorter. Okay, and so this is kind of a kind of an interesting picture for those of us who study gamma ray bursts, but the only way you'd ever really hope to prove this, that these things are mergers, happens to be detecting gravitational waves, right? So gravitational waves have that very characteristic signal I showed very early on, that sort of chirp, ringing down signal. So if you could actually find a gamma ray burst and a gravitational wave signal at the same time, that would really tie together this picture of mergers as being the explanation for this thing, gamma ray bursts. So you can see how someone like me who studies gamma ray bursts is really interested in gravitational waves to sort of further my understanding of these things. Likewise, people that study gravitational waves really wanted this connection to be true so they could find the electromagnetic counterparts to sort of hammer in the reality and the veracity and usefulness of gravitational wave signals. Okay, so to summarize, short bursts, short duration bursts shown in blue, we think are largely due to the mergers of compact objects, perhaps neutron stars, and we think those produce gravitational waves, and lo and behold, that's what we saw, okay? So to back up to the first slide, just so you remember, that was a discussion of the little movie, was a discussion of the first gravitational wave signal, right? I showed this kind of time series here in two locations, Louisiana and Washington, how they kind of match each other, and how if you look at it in frequency space, it's kind of a chirp. And this is all predicted. These are the models actually plotted over the data. The models extremely accurately predict. This is just the pure model right here of this event in spiraling and merging. The models very clearly match the data, right? You get this sort of signal envelope that's increasing in intensity, it's chirping, and then it's ringing down, right? And so that, for this first detection, was a pretty clear sign that LIGO was seeing actual astrophysical gravitational waves from astrophysical sources. And they didn't see this a lot. You might, at this time, we were really worried about, spurious signals, a truck drives by, can make a spurious signal. But this thing is so closely matched to theory that it has a chance rate of being extremely rare, sort of once in a couple 100,000 years, right? And it's modeled in this case by two very massive black holes, 36 and 29 solar mass black holes, right? So this was the first detection in 2015 of gravitational wave sources. Fits theory super well, looks really exciting, but yet doesn't have this sort of proof in the pudding that astronomers want, okay? So to prove it's real, and what I mean by that is if you think about this event, it was justified or thought to be real because it was very rare and because it very closely matches the predictions from theory, right? So if you didn't know those two things, LIGO gets all kinds of funky signals through it, all sorts of noise, right? To really go after the thing you're interested in, has to sort of have these two properties, okay? But that's not enough for a lot of scientists. So what do we want? We want to see the electromagnetic signal, right? We want to see the gamma ray burst, or we want to see the fading source that tells us there was something that blew up at that part of space. So that's also exciting because it allows us to connect up all the existing astrophysical knowledge we built up over a long time about black holes, neutron stars, et cetera, and specifically the stuff I've been talking about with respect to gamma ray bursts, right? And so how do you do this? How would an astronomer like me prove that this thing's real? We need, and we use our optical telescopes to point at these air regions and to look for a source that's consistent and coincident with this explosion, right? And it's a hard problem. And it wasn't just an immediate result when 2017, the thing that led to the Nobel Prize happened. Many of us were working on this for quite a while. And this is a map of the Earth to give a sense of the uncertainty of the position of one of these gravitational wave events. So they're huge on the skies. Typically, the common gravitational wave region is a few hundred square degrees, and they have these kind of exotic banana-like structures on the sky, okay? And it's very hard as a ground-based astronomer to point your telescope at such a huge region of the sky, so kind of moving it around, taking pictures, all the while looking for some sort of new source, right? Not being guaranteed that source is going to be particularly bright, but having to search a really huge part of the sky to find it. Okay, so if you're familiar with big telescopes have very narrow fields of view, right? Typically few arc minutes, whereas the full moon is about 30 arc minutes across. So it would take many, many pointings with a large telescope to cover 300 square degrees, right? And so one strategy you could actually try to do with a large telescope is you might not try to cover the entire sky, but maybe you just look at the bright galaxies, right? We know that the gravitational wave signal can't be detected if it's too far away. Most of the galaxies are known within that so-called LIGO volume. So one strategy is to point your big telescope at maybe a few hundred galaxies, right, that are within these bright blue regions. That's about kind of a 50-50 game, right? So these are things within a couple hundred megaparsecs. The gravitational wave source might be in one of those galaxies. It might have been from a source that was kicked out of its galaxy because I mentioned there's like 1 billion years of delay between the supernova event and the merger, right? So it's sort of a 50-50 game. It might work. It turns out this did work for the first one that led to the Nobel Prize. Now it hasn't worked much since. So another strategy is using small telescopes. So small telescopes like the ones we saw earlier, like, I don't know if you can see my picture, there's behind me, there's an 11-inch Celestron telescope. That's a small telescope. Nice thing about small telescopes is they have really big fields of view, right, compared to the big telescopes. So a field of view on one of these things could be several degrees, right? The bad thing, though, the small telescope is you have a lot less sensitivity, right? So you can look at the entire sky. In principle, you can look over much more regions than you could with a big telescope. You can look in between galaxies, you can look around, but you're going to have considerably less sensitivity. So you have to do this search fast while the source is very bright. Okay. So let's flash back to this event that led to the Nobel Prize. And what was really unique about this event and why it was so fruitful was because its error region, shown here, was very small. So it wasn't one of these giant bananas. It was pretty compact, and it was such that there were only sort of a handful of well-known galaxies one needed to look at, and it turned out that a group in Santa Cruz pointed at one of those galaxies within a couple hours and found that new source, right? So it wasn't a whole lot of hard work that went into finding this one. And so, kudos to them. Also really interesting about this event shown on the right here is that it was detected in gamma rays, or I should say a gamma ray burst was detected at about the same time as the gravitational wave signal. So the plot here at the bottom shows the gravitational wave chirp. The time 0 is set so that it's sort of the end of the chirp once the merger has happened, right? This is a time axis. And then what's shown in the top 3 panels are so-called light curves, intensity curves of gamma rays for 2 different satellites, Fermi and Integral. And both of those satellites saw this pulse of gamma rays about 2 seconds after the gravitational wave event, okay? And at a consistent position on the sky, to the extent they could say that, okay? So that, in a sense, was the first electromagnetic counterpart to a gravitational wave source. It was a gamma ray burst, a short duration gamma ray burst. It's lasting a small fraction of a second here. And this is what a typical gamma ray burst looks like. It's the typical ones aren't that bright. They're just these little pulses of gamma rays, right? You can see how the noise is at about this level, and the gamma ray pulse is right there, right?
Matt, quick question.
Yep.
How did the why were those possible locations so narrowed?
Yeah, it was an issue of brightness and coincidence of the multiple detectors. It turned out there was something strange that happened with one of the detectors where it was at a weird sort of viewing angle for them. So they didn't realize it right away, but they came back and analyzed their data. And so it was a really nice coincidence in a sense of something being very nearby and being very bright. Okay, so as it gets farther away, it's harder to localize, it's harder to get a good position. These banana regions tend to get bigger, right? And what's also kind of amazing about this, so I say it's kind of nearby, but it's, it's still far away in relative terms. So this was in an NGC galaxy about 100 million light years away, right? So that's still kind of far away, right? We're talking about distant galaxies here, right? So not the nearest couple of megaparsec galaxies, but the ones that are pretty far away, but yet still well known. And an amazing thing, you might say, okay, these 2 events aren't simultaneous, right? Or they're a couple seconds apart. But this is actually phenomenally close to simultaneous. So what this tells us is that the speed of gravitational waves is very, very close to the speed of light. So gravitational waves, as are predicted, travel very close to the speed of light. To a part, it's about 1 in 10 to the minus 15, right? So this is like better than anyone's ever measured the speed of light, right? This is a super, super precise measurement. And the fact that these things are a couple seconds apart is actually phenomenal, right? You think about what a messy kind of explosion this might be. They didn't have to be so close to simultaneous, but this is, for all intents and purposes, in terms of like the size and scale of the universe, this is a simultaneous event. And here's a little bit about the work that sort of we were doing around the same time. So this was the group over here in Santa Cruz who found the gravitational wave source with an optical telescope. As I mentioned, we were over here with Chandra finding this X-ray source at the same position. So right, this is that NGC galaxy. At roughly the same distance from us is this source right there, okay? And really interesting, I won't have a whole lot of time to go into it, but it was actually a pretty strange event in the X-rays. It actually brightened over time, and it seemed to indicate that this was a gamma ray burst that was, so gamma ray bursts are very narrowly beamed, like I showed in the earlier picture with these two cones coming out. And generally to see one, you have to be in that beam angle. But this event was actually indicative of not being in that beam angle. So the event sort of was beamed a little away from us. And then as it sort of slowed down, the beam grows a bit and we're eventually able to see it. So this is a sort of what's what we call an off-axis gamma ray burst, but sort of a strange, non-classical gamma ray burst. Okay, and that's maybe subject for another talk, but kind of an interesting subject. Just a couple of quick things that are kind of cool about this. So one really thing I think is really kind of interesting is to think about where the precious metals in the universe come from. So there are things shown in purple here on the periodic table, things like gold, silver, plutonium, all sorts of fun stuff. That is really hard to make in stars. It doesn't happen via that nuclear process I talked about, which tends to cook up things in multiples of alphas all the way up to iron, right? Producing those kind of metals. These purple things are pretty hard to get because they're atoms which have a lot of neutrons. They're sort of very neutron-rich atoms, and they're just really hard to make, right? And so the picture in the middle here shows some of the ideas for where these kind of things come from. And it was an idea for quite a while that merging neutron stars could be the source of much of the purple in the periodic table, right? And that's essentially because you take two neutron stars, there's a ton of neutrons there, and when you merge them together, those can be squeezed in to make this kind of material. And when it blows up, that material is ejected into the rest of the universe, right? So it's thought that a lot of the gold, silver stuff around us is actually the result of these kinds of explosions. Okay, and this is what I meant when I said, you know, this is a plot of sort of binding energy versus atomic number for this kind of nuclear processes. Stars, you know, are, as they're fusing elements, are building up heavier and heavier things, but once they get to this peak, which occurs at iron, it becomes a process that's not favorable to producing heavier elements. Those things blow themselves apart right away. And so you don't get things heavier than iron. What you really need is this rapid flood of neutrons. So, you know, go blow up a neutron star. Because that's kind of a fun side story. Okay, but in the time I have left, I want to shift over and talk a bit about what we're actually doing. And I want to focus in a bit on software because this essentially becomes kind of a challenging software problem. So chasing gravitational waves. So what are we doing here? So we're using quite a large number of small, medium, and large telescopes to chase these signals from the ground. Okay, the small ones and the medium ones as well are fully robotic systems. Several of them that I'll be talking about today are at an observatory in Baja California, Mexico, called San Pedro Martir, just kind of across the border from San Diego. I'll talk a little bit about an experiment called RATIR, which is the Reionization in Transients Infrared Camera. This is an experiment designed to go after gamma ray bursts. It's ending in a few months and will be replaced by a new system called Colibri, or Hummingbird, which will essentially do a lot of the same stuff, but in a more modern and rapid way. There's also a half-meter telescope called Coatli, which is a sort of a kind of like the system Tom was talking about at the start of the presentation today, where you kind of stack images real fast. Here we're trying to stack images so fast that we are compensating for disturbances in the atmosphere. So sort of kind of trying to do something like adaptive optics to get very fine images. And then one I want to talk mainly about is called DOTI, the Deca-Degree Optical Transient Imager. This is a system, or hold on a second, this is a system of multiple of these Celestron 11-inch telescopes like the one behind me, just sort of scaled up and really pushing the limits of what you can do with a small telescope if you just sort of sit on the sky and you try to monitor the sky. So scale it up, put it at a world-class observatories. And a point I want to make is that the big telescopes out there that astronomers use, that I use, sort of 8-meter plus class things, Hubble, Chandra, space telescopes, right? You can really only use them in this game once you've had the small telescopes come in and give you the positions to point your big telescopes, right? So there's a real important niche the small telescopes, the largely robotic telescopes fill in order to find the positions of these sources on the ground. And then we can do big telescope science, okay? But that really depends on these small telescopes. Okay, so let me just mention Ratier. This is the one I said was ending. It's been a lot of fun. It's been online since 2012, around the time I first came here. It's a 1.5 meter telescope that does imaging in 6 colors from the optical through the infrared. What it's trying to do is find a new source, like this little dot I show here. That's actually a gamma ray burst afterglow. It's trying to find a new source that's present in the infrared, but absent in the bluest images. And that's the signature of something that's cosmologically distant, very cosmologically distant. This case, an event at redshift 6. This is when the universe was 7 times smaller than its current size, so quite early in the universe. And what happens at that point is that the intergalactic medium is still fairly unionized, so the blue light gets absorbed by hydrogen. Okay, and so you have this sort of signal called a dropout. And this telescope is meant to find these dropouts very, very fast, within minutes, so that the big telescopes can point at the position and get a spectrum. And then from the spectrum, we can study the ionization history of the universe along the line of sight to this object, right? We can see how hydrogen is ionized as a function of distance, which gives us history of ionization in the universe. This is the observatory, so I'll have more to say about this as I go on. This is the 1.5 meter telescope that Harold Johnson loans to Mexico for $1 a year. It's right here. This is their biggest telescope at 2 meter. On the map here, you can see this blob. That's us. That's Phoenix, right? We're the big light polluters there. Not as bad as LA, but that's us. And then if you look down here, this is San Pedro Martir in a very nice high desert, very dark site in Baja California, Mexico, right? So super impressive site, very, very photometric, very dry, just a lovely site, and kind of a lot of fun too. Go there, you get to drive one of these cool cars. This is what it looks like on a moonlit night if you're looking back to the States, right? You can see California, you can see Yuma in Arizona, but the other side of the mountain is very dark and great for astronomy. Okay, so just to sort of put this out there, a lot of what I actually do in my work is building instruments. So this is a schematic of what this Ratier instrument is. It's comprised of a bunch of slabs of glass that split the light into different channels. So you get that simultaneous imaging on a couple of CCDs in the optical, here and here, and then on infrared arrays inside a dewar, pictured here, held at cryogenic temperatures, down there. Right, and this is accomplished with these things called dichroics. Right, so this is a very custom sort of instrument. It weighs 100 kilograms. It's pretty big. This is a medium-sized telescope. As you go to bigger and bigger telescopes, the instruments get bigger and bigger. As I mentioned, their fields of view narrow, and sort of their versatility narrows as a kind of result. Okay, the other part of this Ratier story is that there's some super serious software challenges associated with this. So we have to receive our gamma ray burst position within seconds. Telescope needs to respond within minutes. So it's got to be able to interrupt whatever it was doing before automatically, schedule its observations, slew to that source. Data has to be taken, and then a pipeline has to come in. That was my responsibility to reduce those data, to stack them, to produce these web pages that are shown here, where new sources, things that weren't known before, are marked in green. Previous sources that are hard to see are in blue. And here you have a stack of all of our colors. This is a historic image from the Digitized Sky Survey. These are our 6 different channels. And so what we have to do fully automatically is find that new source, excuse me, and then the software even publishes the statement that we send out to the community. So we have to be able to wake up in the middle of the night. All our science has to be done for us. we check that it made sense, and then we click send on this email, okay? So this is like what I mean when I say robotic observatories and really sort of robotic science all the way through. Now we do come back and write papers later, but this first report is something that has to be highly automated. Okay, and what I want to do is talk about this game a little more in the context of gravitational waves, and I want to go into software a bit. I want to talk about things like how we go about identifying these sources and how we do this sort of stuff. And it's a big challenge. So what we're trying to do at this mountain in Mexico is a sort of hot wiring process. We have multiple telescopes, various sizes, so different sizes, different capabilities, different kinds of instrumentation. They're all on a common network though, so we can communicate between telescopes, we can share data between telescopes, and we can have them sort of work in a concerted fashion to respond to these triggers and to coordinate observations, all robotically, okay? So this is a huge software challenge. And what I want to do is I want to connect this software challenge to the challenge I've been discussing with gravitational wave sources, where the air regions are huge on the sky, and finding that gravitational wave signal is like finding a needle in a haystack. So we have this sort of robotic network that's producing a lot of images, and we have to efficiently somehow figure out how to go through all those images and find that one new needle, the optical counterpart to the source. Okay, so this is sort of sketching out this complicated software challenge. And what I want to do is also highlight the way the solutions to this software challenge involve all free, all open source software. So these are all things that you can use. As I'll show you, the telescopes are pretty small. This is all stuff you can use on your own telescopes. If you're into astrophotography, this might help you kind of amp it up, take it to the next level. So I want to kind of go through some of these things that I do and show you a little bit about what it would be like to be kind of at the end of the fire hose, sort of taking in data from one of these experiments. So the kind of things we do, image manipulation, right? That's your basic calibration, you know, of your images using things like CFITS.io or PyFits if you're into Python. So that's all free software. I really like a program called Swarp for my image stacking. There's a few other things out there, but Swarp is really nice, really fast. This is for taking images that you've taken several images, you need to align them and then stack them, sum them together to go deeper. I really like astrometry.net is a free package for figuring out where your image is on the sky, right? You have some stars in there, you want to figure out which stars they are, get the so-called world coordinate system of your images. Astrometry.net has a web interface. You can take like a camera picture and you can post it to their site and it'll give you the sky coordinates. Or if you're like me, you need something that runs really fast, they have a C version of that where you can download all the catalogs to your own computer, have that computer sit at your telescope, and you could very rapidly do this kind of analysis. I really like a tool called Source Extractor or Sextractor, written by a French teenager and sort of the mainstream tool in astronomy these days. That's the tool that finds sources in an image. It also does so-called photometry, the measuring of fluxes of those sources. Very impressive tool, kind of been state of the art for a long time, very easy to use. And then I want to talk a little bit about web display tools. This is stuff that is really critical to sort of one of these nightly follow-up campaigns. So how can you display some of this data that's going to allow someone to log in, understand what's happened in your observation, and then allow the user to comb through and find the result, right? So I'll show you a little bit of active kind of pages you can do with Java. And I want to plug a program called Aladdin Light, which you may be familiar with. It's a real nice tool for showing cataloged images or positions in a web page that's on the client side. So it ends up being a really neat thing you can even have running in a remote observatory. Okay, so this is like a software challenge, and I want to sort of spend my remaining, I don't know, 20 minutes or so, something like that, kind of just discussing, going through some examples and kind of showing, you know, what I've had to write in terms of software to help solve this problem and to really enable our observations with these systems. Okay. Set the page, I want to introduce Dottie. So this is a little bit out of date. Initially it was 2 telescopes, now it's 6. This shows the images captured from, I believe we were pointing sort of toward Aquila at this point. 2 telescopes were running. This is about the size of the images. If you think about the full moon again, which is a half degree across. So each of these images is about maybe 3 by 3 degrees. So when Dottie has 2 cameras, and you can see they're generally overlapped a little bit, so we kind of get a consistent sky coverage. And this is a stack of, I believe, 16 images that produce this MOSAIC. And the final Dottie, which I'll go into in more detail, is 6 of these telescopes. So behind me, remember the C11. Dottie's based on similar telescopes, 6 of those on a common mount. So each telescope has this sort of 3 by 3 degree field of view. You get 6 of them. You get about a 72 square degree field for the whole system. So this is covering a pretty significant amount of sky, which is, you know, as I was saying, a good benefit of small telescopes. And it turns out that we can essentially make a movie. We can survey the entire night sky, at least the visible part of the night sky, every night with this system, right? So it's a pretty impressive capability, just built from, you know, fairly standard telescopes that cost, you know, $3,000 or $4,000 each, right? So not cheap. But,
in that, just to underline what you just said, you're gonna have 6 of them on the same mount.
Yeah, let me show you. It's kind of like this.
Oh wow!
So these are what they actually are. They're Celestron Rasa telescopes, and it's like your standard C11, but you put the camera at prime focus. So that's how you get this really wide field of view. You get an f/2.2 camera as a result of that, and so it's pretty compact, pretty small camera here. And then this is what the mount looks like. So it's up on these concrete pillars to get us a little above the trees, right? But we still end up looking through some trees. And you can see the way the mount works when it had 2 telescopes. Now it's filled out to 6, right? So it co-points those 6 telescopes. So they overlap slightly, but basically cover a very large 72 degree square field of view. Okay, so it's kind of like, you know, just really building up pretty standard, you know, backyard astronomy kind of stuff, but kind of taking it to a level where it's, you know, bigger, very dark site, and then trying to make the whole system very, very stable so that we can get very, very precise measurements at the limits of this telescope, right? So if you speak magnitudes, this system can get to mag 19 or so, which is kind of comparable to DSS survey sorts of limits. And it can do that for the entire sky in a night, the visible sky. So that's kind of neat. That's a very well-defined experiment in the sense that we're getting to a depth where everything should be calibrated or cataloged, it should be known, and we can essentially know that if we find anything new, it is something that was uncatalogued, and it can be potentially the you know, counterpart to this gravitational wave source. And then we want to sit on it and monitor it. Okay. So here's a shot of the page of one of the pages of Dottie. And this is all completely automated in software. And I want to stress that it's a real-time reduction system. So as these images come off the telescope, we do about 1-minute exposures. The data are reduced in real time by 1 camera per computer, so per telescope. So we have 6 computers running simultaneously. And they're building up this image, much like the cell phone app that Tom mentioned earlier. We're building up this integrated picture of the pointing on the sky, right? So it has to be a very fast data analysis pipeline. We're talking maybe 20, 30 megapixel images. Each one of these frames has something like 40,000 to maybe 100,000 stars in it. So you have to find all those stars after you produce the very stable image. You have to find out whether it's fading, this kind of fun stuff. So here's a question for those of you with good eyes. Can you, looking at this image, I'll show you bigger ones in a minute, but can you find the one red circle in this image? See if you can spot it, I'll give you a second. So it's up here. So it turns out that in this particular example, we found something like 40,000. This is pointing toward Aquila, of something like 40,000 sources. And these images are so well registered to the sky that we can say that all of those are known. Those are all cataloged sources, except for this one source out of 40,000, right? And it even turns out that this thing was bogus. So once I looked at what this was, it turned out this was the result of a satellite that passed through the image at an inappropriate time. Okay. And so that was fixed later. So this is kind of just to speak to the level of stability we need here. So we have 6 cameras, 6 telescopes. Each of them is finding sitting on a field of view, which might have 40,000 stars. We have to have it registered to the sky so well that we can say whether or not these are existing catalog sources. So we have to know the, let's say, the distortion of each of these optical systems. Each of these telescopes has pretty significant distortion. We have to model that out and correct it at the arc second level, right? So that we can determine whether or not every source in here has a match. There's also a lot of really other kind of interesting stuff. So in a field of view like this of a few degrees, you have to worry about dispersion by the atmospheres. You know, like you stick a stick in a pool, right? It bends, right? Same way with stars, when they come through the atmosphere, they bend toward the observer, so they appear to be higher in the sky. And you actually have to take that physical effect into account, treat it like a distortion, and stretch out your images so they actually align from the center, you know, the frame all the way out, right? So it's actually a pretty good challenge to get a big image like this from a, you know, a consumer class telescope, and then be able to align it really, really well to the sky so that you're not falsely identifying sources out here, right? There could be tens of thousands of sources on the edge of this image. And if we didn't rule those out, no astronomer would be able to look at this to try to find our counterpart. Okay.
Hey, Matt, maybe a relevant comment or question on this was, how do you handle things like other satellites and Starlink and?
Yeah, let me show you. Let me take a brief foray. So this is my backdrop here, just to illustrate. For that same image I was just showing you, let's see where this is. It's in here. That same image I was just showing you was built from 16 frames. And I want to show you what the raw data look like before you stack those. This, I think, speaks to that problem. This might take a second. So this is a program called DS9, which is a really nice image viewer. I have those 16 frames loaded. I'm going to zoom all the way out. Okay, so here you can see it's a raw image. So it hasn't been flat fielded. It has some vignetting. It's darker on the outside. That's an effect we, you know, correct for. But let me match all these frames up. And let me play it like a movie. And just look for some of the stuff that comes through this frame during 16 1-minute exposures. So can you see the satellite trails? There's a good one. There's 2 in that one there. There's 1. There's a big one. Practically every frame, every image that you capture on a camera with a few degree field has a satellite in it. And this isn't even Starlink stuff. This is just normal stuff up in the sky in a dark part of the sky, right? So people that work in this game, we're just used to trimming these out of our data, right? So it's just, it's like every image is going to have 1 or more of these. And what you have to do is you have to basically fit them out and remove them. And so then when you get a series of images, and you can see how the images aren't at the exact same pointing, right? And so when you stack a series of these images by shifting and adding them, the parts that you had to delete from the satellites get fixed. Okay, but satellite trails are a serious thing, right? They're everywhere now. If you try to observe at twilight, you've got Starlink, right? It's really challenging. This is just sort of a way of life nowadays. So all of our pipelines just naturally have to treat these and remove them. So hopefully that answers that question. I'll go back to, actually, I think what I wanted to do is basically do like a little walkthrough. So I want to show you kind of a live page of some of these campaigns. Okay, here we go. This is one of the top level pages from a Dottie observation of a gravitational wave event. Notice it kind of looks like a bunch of squares. Each square is 1 camera. And so if I count them 1, 2, 3, 4, 5, 6, it's 6 by 6. So I told you that Dottie was 6 telescopes. So this is 6 separate pointings of Dottie to cover a big region of the sky. One of the Dottie simultaneous fields of view is like one of these regions I'm showing here. Let's see if I think I'm allowed to draw on it. It's like this, right? A little 2x3 region. That's the 6 telescopes. So here's another one right here, right? And then that pattern repeats here, that pattern repeats here. And these are actually, these are stars, right? These things, this is an actual image, and it has, you know, each one of these little squares has maybe 500,000 stars. You got what, 36 of them. So you're talking, you know, a lot of stars, right? That have to be cataloged and identified to find the potential new source in this huge region of the sky. And this is interesting. This is an exposure map. So this shows how we kind of exposed on that part of the sky. And if you look closely, you might be able to see all these lines, right? Those are satellite trails. Those are all regions that had to be removed in order to produce this fairly clean mosaic of that very large part of the sky. Okay. So, you know, you're an observer, gravitational wave event has gone off. You're using Dottie to follow this stuff off. This has all happened automatically. This page has been generated and it's being updated every minute or so as new data come in. What we typically do is we tile over this region for about 10 minutes, and then we come back and start again because we're looking for a source that's perhaps fading, right? The observations are broken up into visits. So a visit is a pointing. So let me go into the first visit. So basically what I'm going to do is I'm going to dig deeper and deeper into the data as I click here. So this is sort of just a top level view, but what I need is this tool to essentially allow me to find that needle in that haystack. So let's go into visit 0. And when you see visit 0, what you're going to see are the actual images from the 6 Dottie cameras. We had an error region from the source that's shown in green here. It's a little kind of off-centered. And at this level, we start to get statements about whether or not uncatalogued sources are found, right? Whether they're bright or they're fading, this kind of information. In this case, of all these 6 frames, no interesting source was found. That's kind of impressive. So these are exposures of, in some cases, you know, these are over 1,000 seconds. So these are tens of minutes. We're reaching 20 plus mag or so. So we're going pretty deep. And if I look at some of these, so this, I can drill down farther. You might be able to see some kind of red circles happening here. Let me maybe pick one of these out. I'll pick this one. So when I clicked on that, it zoomed me into the camera itself. That's camera 1 for Dottie. And you can see it found some sources on the edge, which I bet aren't very real. Found this thing, which it thinks is kind of interesting. Okay, and then it has some data on these sources. They're all flagged as questionable. Okay, and that has to do with basically some weird stability effects that were observed. You know, when things are at the edge of your chip, they can often be measured poorly, so they're really not real sources. But this one is kind of intriguing. So let me just look at that. So what I do is I just click on it. You can see when I mouse over, I get a position on the sky. Here I'm using some Java to overlay all the known cataloged sources in blue. And this is my new source here in red. So I go over it, tells me a little bit about how bright it was. And then what I have on the right here is that program called Aladdin Light, which allows me to do a client-side catalog image. This is from the Pan-STAR survey. Okay, so this is the same part of the sky measured by our experiment, and here measured by Pan-STARs. And what I can do is I can blink these. So I can hit this button called Switch Images. So what I want you to do is I switch them, is I want you to keep your eye on this part right here where my new source is. And we're going to try to see if it's truly not present in the cataloged image. So I'm going to do Switch Images a few times. So do you see how most of the stars are present in both images? Right? The quality is a little different. Blurriness is a little different. But for the most part, you know, things are there in both images, everything I put a blue circle on. But that red thing is much brighter than, there might be a faint little, maybe there's a faint little thing in there, barely visible, but it's clearly much fainter than this thing we see, right? So I can try that. So this is a source. This is designed to kind of let me drill in and check stuff out. So if I click on this button down here, I'll get a light curve. right? So there's a time history of this event. It's actually perhaps fading a little bit. So you can see we observed this over a couple hours, right? We kept coming back to it. And so it's got this time history. That's generated by taking that stack of frames. After you align them all, you run source extractor over them. You do really accurate photometry. And so you can try to ascertain whether this thing is fading, which would be really exciting to us. And this thing is in fact fading very marginally. So this line is actually tilting down a little bit with an error bar almost as big as the tilt. Okay. And then you can even explore a little more. I'll close that window. It lets me. You can click to see whether or not this is known in the so-called transient name server. So we click on that. This is a site run out of Israel. They maintain sources. And it turns out this source actually was a known transient called AT2021RJV, detected by Atlas in the ZTF survey. So this is an astrophysically kind of interesting source, and it is in a sense something the kind of thing we're chasing after, but someone found it before us. And it's not, in this case, associated with the gamma ray burst. This was discovered quite a while before the event went off. Okay. But that can be contrasted with everything in blue here. So everything in blue here is actually a known star from the surveys we query. Things like, so we query pan stars, we query USNO, we query DSS, we query Gaia. So we look, and TUMAS, we look at all these different surveys to identify and positively ID all these stars. So if I click on that one, you can see this source has a pan-stars 1 DR1 magnitude of 20.5, right? Which is pretty closely in agreement with the 20.08 we measure, right? And take another source over here. That source is a Gaia source with a magnitude of 13.7, which is real close to the 13.6 we measure. So every source that's in this image has been matched to a catalog, right? And so the way we do that is we have all these catalogs downloaded at the mountain, right? And so we can query them in real time after we produce our images, find all the stars, and we can produce all these little circles and really kind of go in here and identify the sources of interest, okay? And so the kind of part of this that's so challenging, let me just click like a random part of this field of view. Every time I zoom into this, you're gonna see, things aren't always perfect. There's some defects and stuff. I think we look cleaner than these guys over here, but there's just a lot of sources in some part of the sky like this. And so we have to identify very, very consistently which of these are known sources and which of them are potentially interesting. Okay. And some of the cool Java stuff you can do here is you can kind of mouse over these. You can turn off all the sources if you want. It's a program, this is a package called Map Highlight, which is really neat for making active images. And this Aladdin Light program is really neat. You can display other surveys. So you might be interested in looking at the Z-band survey from DR1. So it'll overlay another survey. I like the reverse color map. That allows me to look at another kind of filter. So that can be really handy if I were finding a source that, let's say I was interested in this potential source. I might want a Z-band survey so that I could look for a source that was very red. Maybe it didn't appear very bright in the regular pan-stars survey and the R-band survey, but it was very bright in the Z-band survey. So in those cases, the little red circles I've dropped are probably just noise. They barely look like stars to me. They're sort of at our threshold, and I don't see anything in the other survey. Okay. So this is kind of what we do. So, in order to do this kind of science, we need to be able to look at potentially hundreds of square degrees of the sky. We have to have it all done by machines. And essentially for me, this became a challenging software problem because I had to be able to write a pipeline that would very consistently be able to combine these images and then summarize all the data in a way where I had maybe a handful of candidates that I could look at, I could click through and check out of potentially tens of millions of potential stars. So if I had not done this correctly, I'd misaligned, as I mentioned, you could get thousands and thousands of false alarms on the side of your image. Like In this case, I got a few false alarms. I click over there, you can see that image is getting really nasty out there. Or maybe that actually, I think that's actually probably the edge of a satellite trail. It wasn't correctly subtracted, right? So at the edge of your image, you can get weird stuff happening. Okay, so you can't get rid of everything, but you can get these things to be much, much cleaner than you might expect at first blush. So that's an example of one campaign, right? When we do this, we have this outermost level with all these images. We click through by visits. We get a summary of whether there's an interesting source in any visit. We can also immediately see whether the data quality are good enough. And click through and check out some of these sources. There's a bright star, right? We found really fun stuff just doing this kind of thing. You find like comets and stuff. You find a lot of asteroids. So a lot of the things that are found are moving sources, and those are cataloged. So we query them and we can reject them. But it's kind of neat to see in these images asteroids because they're kind of like stretched out stars. So let's see, that was one campaign. Let's see how I'm doing on time. Maybe I'll show you just a couple of quick images. This is another fun one just to show you that kind of all look the same, right? This was another 6 pointing field. The exposure maps look pretty wild. Tons of satellites going through in this case, right? You can see they tend to go across multiple cameras, right? So a satellite really streaks across the whole sky. And we produce these huge images that have just gobs and gobs of stars. Click on them, I'm zooming in. Right, so let's see, it's a little hard for me to see the little red circles, but in this case, so 72 square degrees, it found nothing of interest. These things tend to be spurious. Let me maybe click on one. Let's see what this object is in here. Let's zoom in on that. This is just getting to be kind of crummy data quality around these sources. You can see these kind of stripes, these bad quality things in the image are producing some false alarms, right? But none of those are flagging because we get time histories for all those. This is probably actually a moving source. This is what asteroids look like in our data. They tend to get brighter and then fainter as the source moves in and out of your aperture. So that source 5096, kind of see it in here. This is like what a moving source looks like. So this actually is an astrophysical source, but it's nothing we're interested in. It's been identified with a known asteroid. Okay. So just to kind of summarize there, this problem of searching over a large part of the sky to find a new source is literally a needle in the haystack problem. You're trying to find that one needle out of millions and millions of known sources. To do this, you really have to solve this software problem of being able to keep up with your data as it's coming in, to be able to compare to past data in these catalogs, and to do so in a very highly consistent fashion where you're rejecting all the sort of false alarms, right? So you're in principle able to find that 1 in a million source of interest. Okay, and we have been successful using this to chase gamma ray bursts, but we have yet to be successful to find more gravitational wave sources. Okay, so let me go back to the talk. It's really, I would say, a key aspect of this field right now that we had the event in 2017, which led to the Nobel Prize. It was unique, it was bright, it was nearby, and in subsequent LIGO runs, and we'll have another LIGO run next winter, we haven't found more of those. So we've gotten more of these binary black hole systems. We haven't gotten more of these merging neutron stars with a clear electromagnetic counterpart. So although this was a very exciting area that we thought might have been sort of blown wide open in 2017, it's turned out to be a very, very challenging game, and one that I really call a software challenge, because you really got to be diligent about pouring through gobs and gobs of data. Okay, looking forward. So let me move to wrap up here. So we're sort of in a regime already where transient surveys and robots are really mining the night sky. The example I showed was, I don't think too far removed from what you might work with, with your own telescopes, just sort of putting some maybe different types of cameras in front of them and spending some more time in software, but small, very small telescopes. And then this game is kind of building up to the very, very large telescopes. So coming online, not too far from now, is the Large Synoptic Survey Telescope shown here. So this is a giant telescope, really, done in Chile, and there's a person here for scale. This is a telescope that's basically making movies of the night sky, but at a much, much more sensitive limit. So the LSST is going to find literally hundreds of thousands of new unknown sources every night, right? So whereas Dottie was a very well-defined experiment where everything we know we're going to see has either been cataloged or it's new, the LSST is sort of looking beyond all that to much more distant parts of the universe where a lot of the things it sees, it won't know what they are. So it's going to be a real challenge to not just dig into LSST data, but to point other telescopes in this robotic network that I've been discussing at these sources to try to understand what they are. It's going to get really interesting. LIGO is continuing to go, right? I would very confidently say that it's a much harder game than we thought it was going to be in August of 2017. Next run is in a year, so stay tuned. We have all these systems that are up and going, more coming online every day. And LSST is just going to be nuts. So we're going to have sort of this GRB type game, which happens once a night. You have an interesting event. LSST is going to do this 100,000 times a night. So it's going to be a real phase transition in this whole kind of science, finding all sorts of new stuff, GRBs for sure, probably gravitational wave sources if we're lucky, but probably all kinds of novel transients we've just never imagined. So it's going to get kind of wild. So stay tuned. There's all sorts of fun ways to follow along. Check it out. I think I'm done. Let me just say that last point. It's a whole new kind of astrophysics coming on.
Well, thanks, Nat.
Sure.
There are a few questions. Just dwelling on the last few slides you had, it looked like you were via software detecting possible changes in your cameras, in your images. Are you saying that it's still manual to go and weed out which ones are real and which ones are false alarms?
Well, it's manual at the level of, I would say in a campaign like that where we observe hundreds of square degrees, it's completely automated in the sense where it gives you very high quality data and gives you perhaps 3 or 4 candidates to look through, right? So it's whittled it down from 3 million to 3. It's sort of that level, it's very, very stable. Turns out that the 3 you find could be spurious things, right? You do every once in a while have something that wasn't removed from your image properly. You have some artifacts that can happen. You have a lot of astrophysical stuff that happens, like asteroids, comets you see occasionally, right? Things that aren't cataloged well enough, that maybe the position's not perfect in the catalogs, right? So you misidentify. So it's when you're drilling into this sort of 1 in a million level, it's a very, very high level of precision, right? And so I would say the cameras are incredibly stable, but even getting to the point where we rule out everything is just such a monumental task.
Yeah, I mean, how do you do that in real time? Because, like you said, it's sort of transient, right?
Yeah, so you flag everything that you know exists, right? You catalog it, you sort of dump it, right? You slash and burn. For the things that are interesting, you see if they're fading, right? You try to see if they are actual transients. And so those you're going to highlight, make them blink right to the observer. And things that are otherwise interesting, maybe they're not cataloged, or maybe they have a weird time history. You sort of try to make those apparent to the observer. So you're really trying to slash and burn through a ton of data to sort of alert someone to some interesting possibility. And it's very different from sitting at a telescope and actually looking at images, right? Or processing your images, right? This is very downstream from that, where you're basically at the end of a process and your job is to validate that process, to look through maybe a couple images.
How long do you have after you identify something? Do you have before it goes away and it's too late, nobody can point?
Yeah, so GRBs, that could be with, we want to get on in minutes. That could be hours, a few hours, it becomes kind of worthless. We're trying to do stuff same night. You really can't wait till the next day. So you're trying to get your result out essentially in real time.
So do you have teams of people that are always manning these?
Yeah, we do. Yeah.
Okay.
We have, various observatories. Swift has its people that are sending alerts out. We have people that are on, depending on also what sort of large telescopes we have access to on a given night, we'll have people, on duty sort of to speak. And yeah, so.
But I mean, your DOTI system though, you have to have that staff.
The system is robotic, doesn't even need anyone to close it, but we do have students who are logged into Skype, whenever we know we have a campaign going on, to sort of watch the images as they come in.
Okay. Let's see. So yeah, let me go back to some of the questions. So Bill Galladay, he's being stickler, even though it's 1 part in 10 to the 15th for the gravitational wave and the light wave to reach the Earth, still 1.7 seconds. Is that within the instrument's lag time?
No, it's real. It's real.
It's real. Okay.
If you think about what this physically is, this is a messy thing, right? This is like two compact objects which merge, their surfaces are touching, they're ripping themselves apart. Somehow an accretion disk and a black hole is formed and this pulse of light goes out. Why that should be 1.7 seconds and not 5, who knows? But the fact that it was close to 0 is the thing that really matters. We have a very stochastic, messy process.
Okay.
Next time we see it, it might be 10 seconds,
All right, so David Kausho, he has a question about the mirrors. David, do you want to ask your question live? Let's see. The question, do you have to refigure your mirrors? I don't completely understand.
For Dottie, no, Dottie's just off the shelf.
Okay.
Dottie has, the Celestron Razas are just off the shelf. They have a corrector plate. If you have an old like Celestron, you can buy like a prime focus mounts down in Tucson for them. They're pretty cool. It's all just off the shelf stuff. It has a lot of distortion. It's just barrel distortion that's common for those kind of systems. It's very consistent though. You can take it out in software.
Okay, and Bill was asking about how you deal with all the asteroids. I think you talked about that, but I don't know.
How do you do all the asteroids?
Yeah, there's some good servers you can do. I use a program called Skybot that gives you, basically tell it your time you're observing, where you are on the Earth, and it'll give you a list of the asteroids that are in your field of view. Minor Planet Checker is another really good one if you want to pull out a bunch of candidates and compare against a list. So these are all webs. There's a bunch of really awesome web services out there that allow you to compare to existing catalogs of known stars, of things like asteroids. And in this game you have to rule out a lot of asteroids. In one of those campaigns there are probably 1,000 asteroids.
I'll add into Bill's question. Do you find many new asteroids that aren't known, and you add them to the catalog?
We have
No.
The ones we see are cataloged.
Okay.
We haven't really dug deep though. The level where if you think what an asteroid is, right? It's a moving source. So it has to be pretty bright to look like a static source, or it has to be not moving very fast. And so I don't think there's a whole lot of parameter space there for such a small telescope. So we're not really probably that good at finding new asteroids.
Okay, then Tom Curry was asking if you're working on machine learning to help the search.
Yeah, it's sort of on and off. So here, some of the places the machine learning have been really useful is trying to get better source detection. So we do image subtraction sometimes to find sources around big galaxies. That tends to be a very weird, messy process. And there's been some luck using machine learning to rule out false alarms with that. Most of what I'm doing here though has to be, I kind of have to have a process that's deterministic. It's got to run super fast and give me a result. I can't really go fishing in the data. I can't do a fishing expedition with machine learning on this kind of stuff. after that we get a bunch of data, then machine learning is probably really interesting for finding new classes of objects, maybe looking for faint asteroids, doing that kind of stuff. But machine learning isn't something we throw at the data in real time.
Okay, then Thomas McGrath, do you have a question?
Yeah, it's actually I wrote it fairly long, but basically it's it would be 40,000 images or 4,000 items in a single image or whatever. There's some number going to be actually naturally variable. How do you actually determine because the catalogs don't know that, oh, this is an eclipse in the binary or this is something else or whatever. How close in magnitude do they have to be before you actually say, oh, it's a real thing or it's just exactly the same position?
Yeah, that's a good question. So I think something like 5% of stars vary at 5%, right? Everything kind of varies if you get sensitively enough. And luckily, the kind of stuff we're chasing after here are really highly variable objects. So these gamma ray bursts are varying by, orders of magnitude over timescales of hours, right? So sometimes we'll see a source, it's varying. But if it's, varying up and down, if it's just oscillating, we can rule it out based on the kind of statistics we calculate on the light curve.
So if it's like 10% the brightness or 10 times the brightness, so you're like, that's not what we're looking for.
Yeah, go pass that guy on, right?
Yeah.
If it doesn't have a kind of profile we're looking for. So we're kind of in this game, we're really looking for things that are new, right? They're pretty dramatically different. And the place where that gets tricky is it could be something real close to the noise floor. So there is a little bit of degeneracy for things that vary a little bit and might pop up and down, right? But those aren't kind of like you were mentioning, the stars that just vary. Those are like bright things that just kind of burble. We can roll that out really fast, right? Because that's a cataloged source. We're not interested in that. We would be looking for something that kind of was new, might be real near the noise floor, but at that level, there's not good enough statistics. Stars aren't varying; they're basically constant, right? Stars don't vary.
Is your data available for other? I haven't done research in 20 years, but I remember like trying to grab all the data we could when we'd find we're trying to get magnitude curves and stuff like that. Is your data available for people who want to, like, oh, hey, he happens to have just observed something in our field of view?
Yeah, no, it's not been so much because we've been focused on this kind of couple of narrow kinds of problems, right, where we do pointed observations. But I've been really pushing for producing this sort of catalog of the entire sky, this time variable catalog of the sky, right? Because we do it. We are, monitoring the whole sky basically. So I would really like to see this stuff just go into, summary, maybe not images. That might be a lot of data to share, but I could certainly imagine sharing catalogs of all the sources and how they're varying in time. And so one of my goals has been to make all these data products such that they could be really rapidly searched and, kind of compared to one another. And who knows, maybe there's some funding for that. That hasn't been like a key focus, but in principle, it's doable.
Yeah, thank you.
Yep.
Sorry, Claude, you were wondering about the field of view and compared to Vera Rubin.
LSST Rubin is something like, oh gosh, I feel like it's about 8 degrees across, something like that. So, we're talking with our small telescopes, a significantly bigger field of view, but we're only, 11 inches and not meters.
You're saying what, 75 square degrees for the pair of them?
For 6 of them.
Oh, for 6 of them.
Yeah.
Okay.
So, Rubin is neat and it's so sensitive, but what Rubin can't do very well is it's very, its cadence is very sporadic, right? It has to kind of pop around and only occasionally come back to a source because of the field of view. It's not a huge field of view. It's huge for a comparably sized telescope, but compared to like the whole sky, it's not super huge. And so they have a pretty stochastic, rarely sort of coming back to the same part of sky survey strategy. So it'll be interesting. It'll be challenging that way. Like you don't get to like just sit on a part of the sky and watch a source, how it fades or brightens. You kind of go away, do something else and come back.
So do you scan the whole sky periodically when you don't have alerts?
Yeah, so what we've been trying to do for the last year is build up basically a whole sky image to the depth we need. And so then when we come back to the next season of LIGO events, we can actually compare an image taken this year to one taken last year, and literally see in pixel space whether something's new. Well, that allows us to do image subtraction.
So LIGO's down now for upgrades and modifications?
Yeah, 04 is starting earliest, something like December of 2022.
Okay. Interesting. Let's see if there's any more. Okay, let's see, Woody. Let me unmute Woody. Go ahead, Woody.
Oh, okay, thank you. Hi, Nate. What cameras are you using on the rasoscopes?
Yeah, so these are, I think I mentioned it in one of the slides. Let me see if I can bring it back up. These are from Finger Lakes. So we're using these Kodak-based cameras. Where's my presentation? Let me open it up and then see if I can share it again. Oh, I think I'm actually.
Yeah, sorry, I think I took you out.
Yeah, I will share it real quick. So I'll give you the item number here. Let me go to the end where I had that slide. I think it says it here. Yeah, so these are microline, and they use this Kodak. It's just a front-sided CCD 50100. It's got like 6K by 6K pixels. They're pretty big pixels, so we have like 2 arcsecond pixels on the sky, which is, a little suboptimal for what we typically have in astronomy, but it allows us to build pretty big fields of view very efficiently.
Would CMOS cameras aid in this with the much more rapid download time?
Yeah, I mean, CMOS-y stuff's pretty cool. So we use, like the infrared camera we use are very sort of CMOS-y in that kind of sense. So there's some advantages. And, at this point, I don't think there's anything majorly different about CMOS and CCDs. You can do about the same thing with one or the other. This would certainly be benefited by either a higher quality CMOS or CCD detector, a backside illuminated device or something with a little more stability.
Okay. How long do you dwell on a single point in the sky before you slew to another location?
So we typically do 1 minute exposures, and you need at least, say, 3 of them to get good sort of bad pixel rejection and get a good clean image. So at least a few minutes, typically 10, 20 minutes. And then we'll, basically move around and then come back to a position on the sky at about an hour later, which is maybe a typical sort of time scale to look for a variation in flux.
Okay. All right. For example, I have a single C11 Edge HD with a hyperstar. So the star is on a version of your RASA. Could that single system be put to use in your investigation?
We are trying to build more of these. So this system is up and running, and it's actually a lot of work so they are really interested in basically keeping everything like the same on these things, because it's a lot of work to maintain the little computers that run them, to the focusers that make them work, to the mounts and stuff. So they like to have them be very interchangeable. They are talking about putting one of these in France and somewhere else. I forget where exactly. Maybe, yeah, I forget where. So it's in principle something you could replicate. It's not that challenging, although the mount is a little bit of a beast. I did try to get these guys to run some different cameras on them, but they weren't super receptive. I wanted some infrared cameras on the fronts of these.
So Woody, I think you're asking what would it take to get a system thrown on your scope, right?
Well, I've got spare time sometimes when I'm not doing spectroscopy with my main OTA. So I have this C11 Edge mounted as an additional OTA on my mount.
Cool.
And, the times that I'm not doing spectroscopy, maybe I could put it to productive use running this hyperstar system where I don't have to be paying such close attention as I have to when I'm doing spectroscopy.
Yeah, you could try a little bit of software out. You could try to jump into this game.
I use Aladdin and Sextractor and astrometry.net and some of the tools you've mentioned, but
cool.
Thank you.
Yep.
Okay, I think that's the last question I see. Well, thanks, Nat. Now we know what a needle in the haystack looks like in the sky. It's pretty tough. But hopefully, when LIGO gets back up, you be able to find some of these.
Yep.
Okay.
Glad to be there.
Back to you, Claude.
Oh, thank you, Nat. I really appreciate it. That was a great presentation and lots of information, not just about LIGO, but about the process that you're going through. Really, really interesting. So I appreciate it. I did get a note from Tom Curry that the SAC site website is having some issues, so they may not post data until after the 26th. But if you're still online, whenever you have more information, let us know. We'll put it out through the EVAC channels as well. So look forward to the Messier Marathon. And we'll see you again for our next meeting, March 18th. Don't forget the telescope demo on Saturday night at Greco, and the other things that we mentioned, the other lectures at Tempe, and also the Outdoor Expo. Lots of fun things going on. I hope that you're having some good days of viewing now that the clouds have gotten better or less than they were. And we'll see you again on March 18th. Thank you.